The second part of 5.3 is more points of concurrency. So the median of a triangle is a segment whose endpoints are the vertex and the midpoint of the opposite side. So here's a vertex, here's the midpoint of the opposite side, and connect them. I didn't do a very good job keeping it straight. So start at the vertex and connect the midpoint of the opposite side. Start at the vertex and connect the midpoint of the opposite side. The point of concurrency of the medians is called the centroid. So up here, Theorem 5.8 reads the centroid is 2/3 the distance from each vertex to the midpoint of the opposite side. So again, I'm going to draw out the centroid. So this is a midpoint, connect it. I'll try to be straighter. This is a midpoint down here, connect it. This is a midpoint over here, 1, 2, 3, 1, 2, 3, connect it. So this is the centroid. So the 2/3, the distance means that this segment right here is 2/3 the distance of the whole segment. This segment right here is 2/3 of the entire segment. This segment is 2/3 of the entire red segment. So sometimes it helps to put numbers on it. So if the blue segment all the way across is 9, so we'll write this as AB. So if AB is 9, that distance is 9, then that means, we'll put a C in here, means that AC is 2/3 of 9. So 2/3 of 9 is 6. So this distance is 6. And this distance is, if this is 2/3, and this is half of that, which is 1/3. So half of 6 is 3. And that works because 6 plus 3 is 9. Let's do it with a couple other numbers. So let's pretend that, I know it's not drawn to scale, but just I'm trying to work with easier numbers. Let's pretend that this is F and this is G. So FG is equal to 15. So if all the way across here is 15, then this part has to be 2/3 of 15. So I write 2/3 of 15 is 10. So this has to be 10. And then this part has to be half of it, which is 5. That's how you set it up. So down here, this has to be a centroid because you're starting at a vertex and going to a midpoint. So this is a centroid. So if you have AD, then AG is 2/3 of AD. Okay, this segment is 2/3 of that. DG must be 1/3 of AD because it's the remaining part. You can also write the relationship half of AG equals GD. That's what's going on. You can do that for each of the 3 segments. I did it for this one, so I'll do one more. So if you have this median, then 2/3 of the distance between E and B is equal to BG. 1/3 of the distance between E and B is equal to EG. And we know that half of BG is EG. That's a relationship. And altitude, so this is another segment in a triangle, is the perpendicular segment from the vertex to the opposite side. And altitude can either be inside the triangle or outside the triangle. So here's an example that's outside the triangle. You start at this vertex and you're trying to hit the opposite side. You're going perpendicular to this. So if you extend this side right here all the way across, this would be perpendicular. So this is why the altitude is outside. If I'm starting at this vertex and I go straight perpendicular, it's right on the triangle. Starting at this vertex and I go straight down, it's inside the triangle. That's why it can be inside, outside, or even on the triangle. The point of concurrency of the altitudes is called the orthocenter. So right here is an example. This triangle on the left is showing altitudes because it's going from a vertex to perpendicular. Okay, that's a little bit, this looks very similar to the circumcenter, so let me draw an example of what the circumcenter would look like. So circumcenter was, not only was it perpendicular, but it was a midpoint. So circumcenter looked like this, whereas, and it never went through it doesn't have to go through a vertex. It could, but it doesn't touch a vertex. An altitude touches a vertex and is perpendicular. So, and this one is bisects, and this one doesn't. This doesn't bisect over here. So that's why this is an altitude. These altitudes are inside, so that's why the orthocenter is right here. So let's review it to the right. The point of concurrency of the perpendicular bisectors is called the circumcenter. The point of concurrency of the angle bisectors is the incenter. The point of concurrency of the medians is called the centroid. And the point of concurrency of the altitudes is called the orthocenter. Which can be outside the triangle? Well, the orthocenter can. And here's an example of how the orthocenter can be outside the triangle. So this is inside, this is perpendicular, you extend here, perpendicular, you extend here, perpendicular, it's inside. This one's inside, but this one is outside. Because if you extended this side, this one would be perpendicular. If you extended this side, this is perpendicular. And if you extended this side, this is perpendicular. And if I made the lines go longer, they would intersect up here, so the orthocenter is outside. Or not always, but it can be.